Derivation of modified Ampere's law. The differential form of Ampere's law as obtained for steady current is incompatible with the principle of conservation of charge when the current is varying with time. The differential form of Ampere's law for steady current is given by del cross B equals to mu naught J. Divide all through by mu naught. We have 1 over mu naught. Del cross B is the same as curl of B equals to J. We can call this one equation 1. Now, take the divergence of both sides of equation 1. So we have 1 over mu naught del dot curl of B is the same as del cross B equals to del dot J. Now, one of the properties of curl is that divergence of curl is 0. Therefore, this one reduces to 0. So we only have divergence of J equals to 0. We can call this one equation 3. And this one here can be our equation 2. But from the equation of continuity, expressing the conservation of charge in differential form given by del dot J plus partial rho plus partial rho partial T equals to 0. Let's call this one equation 4. Divergence of J is not always equal to 0 according to this equation of continuity. It is 0 only when partial rho partial T is 0. Therefore, Ampere's law needs to be modified by adding to the right hand side of equation 2, this equation here, a quantity which will make the divergence of the right hand side everywhere 0. Because as it is right now, the divergence of J is not always equal to 0. That is according to this equation of continuity. This requirement is satisfied according to equation 4. That is the equation of what? That is the equation of continuity. If the divergence of the quantity we add is partial rho partial T. Now, consider the differential form of Gauss's law. It is given by divergence of E equals to rho over epsilon naught. This is the differential form of Gauss's law. Now, let's call this one equation 5. Differentiate equation 5 with respect to time, and then we rearrange it. So we have divergence in brackets epsilon naught. We have multiplied both sides by epsilon naught. Then we take partial E partial T equals to partial rho partial T. Let's call this one equation 6. If we differentiate this equation with respect to T, we get this one. Now, using equation 4 and 6, this is the equation 6. and equation 4 was the equation of the continuity. Now look at it carefully. It was given by del dot j plus partial rho partial t equals to 0. Now using this equation and this one here, as you can see, then we can write, if we take this divergence to the other side, right, we can write partial rho partial t equals to minus divergence of j, right? Now if you look at it, this component partial rho partial t is the same as this component here, partial rho partial t. Therefore we can substitute minus divergence of j in equation 6. Therefore we have divergence into epsilon naught partial e partial t equals to minus divergence of j. Now if you look at this one here, if we add this component, here to the right hand side of equation 1, look at equation 1 carefully. Equation 1 is this one right here. If we add this component to equation 1, then it will make equation 1 everywhere equals to 0. Alright? Therefore, the required Ampere's law is given by 1 over mu naught curl of B equals to J plus this component epsilon naught partial E partial T. Right? Now, here we have epsilon naught and we have the electric field. So we can have 1 over mu naught curl of B equals to J plus partial D partial T, where actually this is the required equation, where partial D partial T is the displacement current and is observed as long as the electric flux vector D varies with time. Thank you for watching.